resolve those issues. But now I think it's a time to move on to the actual materials of the course. So this is the first actual lecture. It's called Introduction to Task-Based Parallelism. And this lecture has 3 primary learning goals. The first is a quick reference to parallel computation and HPC in general. The second learning goal is to understand the very basics of task-based parallelism. And the third learning goal is to understand the theoretical benefits of task-based parallelism. So this is a very theoretical lecture. There are no hands-ons during this lecture. There are hands-ons later today with the OpenMP, but this lecture is meant to be all theoretical and give you overall idea what is task-based parallelism and why you would like to, why it might make sense to learn something about it. So first, a quick refresh to parallel computation and HPC. This is just going to be really short, but I thought it might be a good idea to quickly remind people about the various kind of terminology that's being used. So I went online and I browsed for a good definition for HPC. And I found this definition here from the website called insidehpc.com. And the definition reads as follows. High-performance computing most generally refers to the practice of aggregating computing power in a way that delivers higher performance than one can get out of typical desktop computer or workstation in order to solve large problems in science, engineering, and business. And there are these 3 main terms that appeared here that seems the key. So the first term is the aggregation of computing power. And this is the most simplest one of the 3 to address. In your laptop, you might have, let's say, 4 CPU cores. And then you can compare it to Kebnekaise that has over 600 nodes in a 50 racks totaling over 19,000 CPU cores. So this is several orders of magnitude different in the number of cores that are available for you. The second term, high performance, that pretty much follows directly from the first one. So if you have 4 cores where in these days you might get around 200 billion arithmetic operations per second, compared to Kebnekaise where it's 728 trillion arithmetic operations per second. So again, we have several orders of magnitude difference here in the performance. And this is of course direct result from the fact that we have several orders of magnitude difference in the number of CPU cores at the disposal. The large remaining term is the large problems, and this is sometimes a bit tricky to answer because problem can be large for many different reasons. One reason why it might be large that it just takes really long to solve the problem, and then we may want to introduce some form of parallel programming to attempt to solve this problem in a shorter amount of time by using a larger number of CPU cores. The second reason that might make the problem big is that it takes so much memory or storage to store the data and the output from the solution. And this might make the problem large as well. And of course, in many cases, it's a combination of this both, because when you have a lot of data to process, then it naturally takes much longer to compute the result from that data. So they are not mutually exclusive. When we plot this to concepts here, the memory and storage first on the horizontal axis, and then a performance on the vertical axis, you can see that your laptop is going to land here in the lower left corner. It has some memory and some performance, but not much. Then when you go and buy a higher-end CPU and more memory, then you have a high-end workstation. Then if you have several of these kind of workstation clustered together, you will get a computing cluster and extreme range. Once you have a budget of several millions, then you can have a supercomputer. And in these days, this all would count as a parallel programming in most cases, because even your laptop usually has several cores on these days. But when it comes to high-performance computing, then people usually talk only about the supercomputers, and maybe some people have their own small cluster in their basement, and they like to think that that is a HPC, and that can surely be the case. Then when it comes to these supercomputers and laptops, it's very relevant to talk about different memory models that this system could implement. And the first model is called shared memory. And this is the simplest case where we have a single memory space for all the data. So in these illustrations, you can see these blue balls here. These are meant to illustrate the CPU cores. And then this orange box here is the memory space to which all of these CPU cores have a direct access to. And this makes it very easy to implement because you will just, in most cases, go and access the data. There is nothing else going on there. But then when you move to a more complex situation, you will discover a system that is a distributed memory system. And in this case, we have multiple distinct memory spaces for the data. And usually each CPU core or CPU might have its own memory allocated for it. Or in this case, it would be one node that has its own memory. And the way to access data that does not currently reside in this local memory, you have to talk through the network or a bus. So in this case, you would have two nodes where they have to talk over the network, and this CPU, this node here, will request the data from the node number 2. It will fetch the data from its local memory and send it across over the network. So shared memory, we have a small memory space, things are reasonably simple. But when we move to real systems, we actually have a distributed memory where every CPU or a node has its own memory that cannot be directly accessed from any other node or CPU. And this is the division that you usually encounter when you move from your local laptop or a higher workstation into a small computer cluster or supercomputer, where supercomputers, if you want to use reasonable fraction of the resources, you have to deal with the distributed memory nature of the system. If you are using just your laptop or high-end workstation or individual node, then you can usually assume that you have this one memory space and things are somewhat simpler in that case. What is closely connected here is, of course, the different programming models you might encounter. So in a single core environment, you might be using tools as a MATLAB, Python, C, or Fortran. And the way you write your code is that you have a single stream of operations called thread that is being executed in order. And that thread has access to a single pool of data. So this is probably if you've done any programming and you didn't know what is a shared memory or distributed memory was a threads, you have been doing a single core programming, which is the simplest one to do. Then if you move to an environment where you have several cores, you have to do multi-core programming, which in the simplest case might be vectorized MATLAB code. It could be pthreads or it could be OpenMP, which is something that will be discussed later today. And here the main difference is that you have multiple streams of instructions being executed in parallel, but you still have a single pool of data from which all these instruction streams are pulling information from. Oopsies. And this introduces a couple of additional complications. First, you have to decide how the work is to be distributed. So you have to somehow tell your program that what each one of these instruction streams is supposed to be doing. And then you have to coordinate, for example, by synchronized execution, because if these instruction streams are allowed to run wild, then they might go and access some data here simultaneously and cause all sort of havoc and undefined behavior. So when you move from a single core to multi-core, you will add some complexity in your code. From there, we will move to distributed memory, and there usually is the MPI, message passing interface that is dominating the landscape. And again, you have multiple streams of instructions that you have been programming, but you also have multiple pools of data. So now the data is divided. And in this instance, each one of these threads has its own local data, and they're all talking over the network or a bus to each other. And we have the same complications. We have to think about how the work is distributed among the threads. How do the threads coordinate the execution? But then we also have to decide how we are going to distribute the necessary data among these local memory spaces. And then, of course, there is the communication across data transfers across the network that we have to go and somehow figure out how to do that. Then during the last 10 years, or even actually longer, but the GPUs have been a very hot topic in the last 10 years. So accelerators using a CUDA, OpenCL, OpenACC, or OpenMP. And in this case, you add, again, additional level of complexity. You have a single or multiple streams of operations on a host, which is highlighted here. So this is the main CPU that you might have already been programming. But in addition to these threads running on the host, you have several lightweight threads running on an accelerator device that operates independently from the host. And you must then on all these different layers of memory that are available, because usually the accelerator has its own memory that is separate from the main memory of your computer. And inside these compute units on the accelerator, there is even more memory available. And you must make decisions how do you distribute the data among these memory spaces and how do you coordinate the execution. Then, of course, you can make all sort of hybrids from these. So you can combine distributed memory and multi-core programming with combining MPI and OpenMP, maybe OpenMP and CUDA, maybe MPI and CUDA. And in these instances, you will get a program model that is a hybrid between them. In this example, we have distributed memory, but inside each one of these processes, we actually have a multiple instruction streams running. And these are then running across the network. So the situation could be that you have on a node level, you have, let's say, MPI, OpenMP-based parallelization, and then you have MPI communicating data across different compute nodes. And then finally, we have a task-based that maybe is its own programming model. You might be using OpenMP task or StarPU. And the question is that, is it a programming model? And what the programming model it is? With the OpenMP tasks, you're running on a single in shared memory. So you're basically doing multi-core programming tasks. But when you're StarPU, you can actually do an implicit MPI, implicit pthreads. That is a distributed memory. We have a multi-core, and then we have accelerators on top of that. And this, I'm saying implicit because this is something that is handled by the runtime system. So what you are just doing, creating tasks, and the runtime system is then somehow doing everything simultaneously on multiple cores, on multiple nodes with accelerators. So is it a hybrid approach or is it something completely new? It's difficult to say. Okay, so that concludes a brief summary of interparallel programming and high-performance computing. And it is now finally time to start talking about task-based parallelism. And I would like to start by talking about functions and data dependencies. So let's imagine the following program where we have two functions called function 1 that takes two arguments and it's just going to output their sum. And a function 2 that is going to take just one argument and it's going to output 10 plus this argument. And in the main function, we are setting a to 1 and b to 7 and then call these two functions. And of course, the output is going to be that it's going to print the line, the sum is 17 twice because it's 10 plus 7, and then it's 10 plus 7 coming to the second guy. So nothing special in this program. But you may discover here that in time-wise, when we are calling, then time is moving up to down, and the first function is taking a and b as arguments and reading them, and the second function is taking the argument b, and nothing is being done to the argument b. We can conclude that these two functions are actually independent of each other. So it doesn't matter in which order we are calling this function, it's still going to print the sum is 17 twice. So we could actually run these two functions in parallel, completely independent of each other, because there is no data dependence between them. So this is a very simple example how you could introduce similar parallelism into your software. But if you make things a bit more complex, so what I have done here is simply that the function 1 has been modified in such a way that it will print out the sum of these two arguments, but after that, it will actually increment the second argument with number 3. So in this instance, what is happening is that the b and a and b are being read to the function 1, but then we are also writing to the variable b and then execute the function 2. And in this case, because we have this write happening here, this means that these two functions are no longer independent of each other, because if you execute them in one order, you get the different lines printed than in other order. And if we attempt to do this thing in parallel, then we will actually have a situation where the result is not defined, because depending on whatever order these functions have been executed, or if they're actually executed in parallel, then you will get a different result. So you cannot really guarantee what sort of results you're getting out of your program. So we could say that in this particular context where we are calling these two functions in this order, there is this function 2 is dependent on a function 1. And the function 1 must always be executed completely before we can execute the function number 2. However, this data dependency only exists in this particular context when we are calling these functions in this particular sequence. and giving them these particular arguments. If we would be given them different arguments, then maybe these two functions could be executed in parallel and completely independent of each other. So we can say that the data dependencies are separated from the function definitions. When you look at this, how the functions are defined, and don't see what is happening inside the main function, there is no way for you to tell if these two functions could be executed in parallel or not. It is all the data dependencies that define the dependency between the two functions arise from the data that is fed to them. So just with functions, it's very difficult to know in what order things can happen and what can happen in parallel. The programmer must know in what can run in parallel, what cannot. So what could we do about this situation? Well, we need some sort of, if we would like to somehow automate this thing. So instead of a programming telling in what can run in parallel, what sort of object we need so that the computer could do this thing automatically for us. So the object must be able to do three things. First, it must tell how the computation operations to be executed. So it must define the implementation, what code should run. Then it should define what data is involved. So it should tell you what is the input and output for its operation. And then it would also know that how different computation operations are related to each other. And the object that combines all this information, we call it a task. And in the previous example, we would have two tasks. So the first task, the operation that is going to be performed is the function one. So function one implements the task one. It takes two variables, a and b, as an input, and produces an updated variable b as an output. And it doesn't depend on any earlier task because this was the first operation to be performed. Then we have task number two that is being implemented by function two. It takes a symbol variable as an output to variable b. It doesn't produce any output, and it depends on the task number one. So it means the task number one needs to be executed before the task number two can be executed. And when we look at these task dependencies defined here, how do these different tasks depend on each other? We can represent them using a directed acyclic graph called the task graph. So in this situation, it will look like this. So earlier we had these data dependencies arising from the inputs to two functions. Here we would actually have a task dependency between two tasks that have a certain kind of implementations, accept certain input and output, and then they have this dependency between them. And once we know this sequential order between the tasks, then we can deduce the task dependency from it. So this is indeed what happens in practice. So when you're doing task-based programming, you will basically provide the computer how each task is implemented, and then you will provide it what goes as an input and what is the output of each task. And it is a system called runtime system that will then go and deduce these task dependencies from the information that how each task is implemented and what sort of input and output is coming from each task. And then this allows the runtime system to investigate the resulting task graph and execute all the involved tasks in a sequential consistent order. And here this basically just means that the output of this execution order is going to be equivalent to the output of the program that would execute all tasks in sequentially instead of in parallel. So, but in some cases, instead of letting the runtime system derive the data dependencies, we may want to specify the dependencies explicitly. So you specify how each task is implemented, and then you also say what task is dependent on what previous task. This makes things a bit more complicated, but it can be used to reduce overhead. Because when the runtime system is doing this for us, so the runtime system just knows what is the task, how the task is implemented, what is the input and output, and then derive the data dependencies from it. That introduces some level of overhead to the program that sometimes might be significant. So there are some task-based programs where the programmer instead tells you, this is the way task one is implemented, this is the way task two is implemented, and then saying that task two depends on the task one. In the early examples, this task graph that I showed here was very trivial. So we have 2 tasks, and we know that task 1 needs to be executed before task 2. But in reality, of course, these task graphs end up being much more complicated than this. So let's consider a real numerical algorithm that consists from 3 steps that are iterated multiple times. We do not really care about how each one of these tasks is implemented. We only want to investigate how these tasks depend on each other. So in this instance, we have a matrix, so 2-dimensional array of numbers that has been divided these square blocks. And during each iteration, we start from the diagonal block marked in orange, and we'll do some sort of computations there. Then we will do a second operation that's going to update the blocks on the same block row and the same block column. And the information that is necessary for doing these updates is the information that gets computed in this diagonal block here. So there is going to be dependency from these tasks here to these tasks on the same block row and the same block column. And after we have finished updating the block row and block column marked here in the blue, we will then update this remaining part called training matrix. And again, in order to update the individual block in the training matrix, we are going to need some information from block on the block row and a block column. And then the same process gets repeated to the remaining part. So we'll compute something in the diagonal here in orange. We will update the block row and a block column. There's a dependency. We need some information that is computed here to compute these blocks here. And once we have computed these blocks here, we will need the output of that to compute these blocks in a trailing matrix. And when we go and investigate how the task graph would look like, we will get something like this. So we will do some combinations on the diagonal, and then we will do an updates on a block row and block column, and there is a data dependency from the diagonal block to these block row and column updates here, and these updates here, and these updates here. After we have finished computing the tasks that relate to the block row and block column, then we will go and update some of the trailing matrix blocks. So the situation gets a bit more complex, and now you might understand why you need the runtime system to do these deductions for you. Because here, only thing you have to say to the runtime system is that there is this task here, and this is the input, and this is the output. And the output from this task goes to these tasks here, and then the output from these tasks go to these tasks here. And then the runtime system will automatically go and derive this dependence pattern for you. You don't have to do this manually. But again, it's start to get really complex really quickly. On the left, you can see what you would have if you instead implemented algorithm in a non-task-based manner. So you would have something that looks like this. So you have a for loop that loops over, and every time you compute the diagonal block here, and then you go and update the block rows and the block columns, and then you go and update the trailing matrix. And it's every time you have to compute the entire loop here before I can move on. So you can see that once we compute diagonal block, then we could do the block row and block column updates in parallel. And after those have been computed, you can do the trailing matrix updates in parallel and then move to the next iteration. And you might see how this could lead to load balancing issues, because in order for us to advance along the algorithm in this, if we implement it as a nested for loops, then after you've reached this diagonal block here, then only computations are remaining are these 4 guys here. And if you have multi-core CPU, then it can be very difficult to keep the remaining cores busy, because there are just 2 tasks at this point that could run in parallel. Earlier, we had these several tasks here that we could do in parallel, and everything's fine. But when we move along the algorithm later on, we will just the level of parallelism is going to drop. But if you instead investigate task graphs, so this task here corresponds to this task here on the task graph. And now you know that we actually don't have to execute all these tasks here to advance to this point. We can actually only execute these tasks. And all these tasks here can be delayed. So there is no need to execute them right away. And whereas here, we could just keep 2 CPU cores busy doing some work. Here we can see that we actually have much more tasks that could be executed at this point. So this process of delaying, investigating the task graph and delaying tasks that do not have to be executed at this point can help us later on to keep the otherwise idle CPU cores busy. Then there is a very nice concept that I will discuss next, which is that in this illustration, we have advanced along the task graph to this point, to this task here, by executing only the tasks from which this task depends on and from which this task depends on. So these tasks here do not in any way feed any information to this task or any of these dependencies. And what I've marked here in a red, you can see which is going to be the longest path through the task graph when measured in terms of the execution time. And this is called the critical path. And since every task on the critical path is dependent on one of the tasks that came early in the path, we actually have to execute these tasks sequentially. We cannot parallelize them. Everything here can run in parallel with the critical path, but on the critical path, everything must happen sequentially. And therefore, the critical path, since it's the longest path through the task graph, it is going to give us a lower bound for the execution time of the algorithm. It doesn't matter how much more CPU cores we throw at this problem, it's still the critical path because it's always executed sequentially. The algorithm cannot move any faster than the speed at which the critical path can be advanced. Then I have only at this point talked about how you have the tasks that have implementation, they have input and outputs, and they can have dependencies, but I haven't actually, and how those lead to a task graph, but I haven't really discussed how does the computer actually execute this task graph, and that is the topic that I will be briefly discussing next. So I'll be looking for a different algorithm. Again, I'm not defining how the algorithm itself is implemented. Only thing I'm interested on is that how do different tasks depend on each other. So in this case of this algorithm, we have a sequence of operations happening where we do some sort of operations on the diagonal of the matrix. And so we have the sequence of overlapping diagonal windows. And there is operation happening there, which is called process window, marked here in task graph W. And from each diagonal window, we will get a set of other tasks called write update tasks, are marked in blue. And then we also get a set of left update tasks here marked with the L. And when we look at the task graph, we will do computations on the diagonal, and then we will get the sequence of left-hand side updates that rely on the information that came from the process window task. So there's dependency from the process window task left update task, and similarly there is a dependency from the process window task to the right update task. And again, there is no need to understand any of the details, what the algorithm does and how it's implemented. The only thing we want to investigate is that there are a set of tasks, and the tasks are in some way related to each other to the fact that one task is producing an output that is used as an input to some other task. We also know two additional things about the task graph. First of all, that the process window tasks consume much more time than the left updates and right updates. And then the left updates and the right updates are equally time consuming. And this is actually all the information we need if we want to discover the critical path. And in this instance, for us to advance at the beginning of the task graph to the end of the task graph, the critical path would actually go from one window task to the next left update task, and then the next window task to left update task. So this is going to the critical path. So no matter how much computing power we throw at this algorithm, we cannot advance any faster than the longest path to the task graph. Of course, it is not enough just to execute the critical path. In order for us to advance along the critical path, we also have to execute all the dependencies that the critical path has. So, but it's still going to be the critical path that decides how fast things can move along. It is just that we can use any extra resources to execute the dependencies in parallel. And as long as we have enough resources to execute the dependencies fast enough, then it's always going to be a critical path that decides how fast the algorithm can move forward. In the previous illustration, I have the computer has been executing critical path as dependencies and didn't care about the other part of the task graph, but that is not, of course, always the smartest way to go, because if we have executed these tasks here, then these tasks here, these left-hand updates here, they have all their dependencies satisfied. They need the output of this first window task here, and that to be executed. Therefore, these could be executed at this point. And the same goes for these two write updates tasks here. All the dependencies here has been satisfied at the moment. This write and update here cannot be executed because this write and update here is not executed yet. So we could go and if we have any extra CPU cores available at this point, we could actually go and start executing these tasks that are not at the critical path at the moment, or are not dependencies for the task on the critical path up to this point. But we might go and investigate what happens later, which is that these left updates here, in some point in the future, are going to be feeding information back to the critical path. Whereas this write update here, you look where the output is going, it is not actually being fed back to the critical path at any point. So in some sense, these left-hand side updates here are more important than these write updates here. So we may want to go and somehow prioritize these left-hand side updates over the right-hand side updates, because the right-hand side updates do not feed back to the critical path at any point. So then if we are at this still this point in critical path, we could actually then go and schedule tasks all the way to this line here, because these tasks, all the information that comes to critical path to this point is enough to satisfy all the dependencies for these tasks. And the question is that in this simple example, we could go and make all these kind of deductions that how do the tasks relate to each other. We can identify the critical path and see what would be the optimal way of telling the computer to execute them. But in practice, things get very complex very quickly. So this is a real task graph coming from an algorithm that is closely related to this example I've shown here, but it is just for a very small matrix. So this doesn't really have any practical value. The execution time for the algorithm was just a couple of 100 milliseconds. But in order for me to produce this graph here in a manner that you can see that it's very tiny, it's almost impossible to read, but even this graph here, when the algorithm itself ran a couple of milliseconds, it took the computer several minutes to produce this figure here. So it's not practically viable to go and try to analyze the task graph by yourself and try to figure out that how the computer should execute it. And therefore, we actually need some sort of approach. The computer needs to have some sort of approach for actually scheduling the task graph. And what I'll be talking next is something I'm calling a heuristic scheduling approach for executing the task graph. And the first thing to mention is that, of course, if we know the task graph entirely and we have all the time in the world, then we could come up with the optimal scheduling strategy for the task graph. But this assumes that we know the entire task graph and we know exactly how long each task is going to take to execute. But in real world, the task graph could be huge. It's possible that we don't even have the entire task graph in case we have some sort of iterative algorithm. And then more importantly, we do not actually know how long it takes to execute every task. We could use performance modeling to try to predict it, but in real world, we do not usually have a good enough idea how long each task is going to take to execute. And therefore, trying to come up with the optimal scheduling strategy for a given task graph, it's not usually viable at all. Instead, what the runtime system do, they rely on a different kind of heuristics that attempt to schedule the task graph in a somewhat optimal, close to optimal way, but they avoid the problems that come with the approach where you perform the task graph explicitly. So, and these heuristics are usually based on different kind of list heuristics and priorities that come from the programmer. And the runtime system will then use this information and try to do the scheduling in a smart way. So let's consider a simple example. This is how, more or less, how StarPU functions when you are scheduling tasks in a situation where you don't have GPUs. And I'm assuming that the most OpenMP runtime systems also rely on a somewhat similar approach for scheduling. So we have basically four pools where we put all the tasks. The first pool is called submitted tasks, and it contains all the tasks that are not scheduled yet, and are not ready for scheduling, meaning that we haven't executed them. And it also means that they have some dependencies. They depend on the tasks that came earlier that haven't been executed yet. So it's just all the tasks that are not executed yet, but all their dependencies has been executed. So they would be ready to be executed right now. All the dependencies has been satisfied. And then we have a pool of tasks that are currently active, meaning that they have been scheduled. That is, they are currently running. One CPU core is currently being executed task. And then finally, we have completed task, and this is the pool of all tasks that has been scheduled, and they have already been executed. And if there is some other task that depends on the output of these tasks, then that output data is now available for the tasks that need this data as an input. And the scheduling would look something like this. So all the tasks would start from the submitted pool, meaning that the runtime system is aware that the task exists, but nothing beyond that. And then it's going to basically choose if the task has all its dependencies satisfied, so all the input data is now available, then it will move to the ready pool, indicating that the task is ready for scheduling. And if it happens that some of the input data for the task is not available, it will say in the submitted pool, waiting until the task input data becomes available. When the task is in the ready pool, it will go and check that do we actually have a CPU core or a GPU ready to execute the task. And then if there are priorities, it is also going to check if this task is the highest priority task at the moment. If that is the case, we have a CPU core available or GPU, and this is the high priority task, then it is going to be scheduled on resource. So the CPU or GPU will start executing the implementation of the task. If not, it will stay in the ready pool. And once the task has been executed, it will of course move also the active pool. So the runtime system knows that this task is currently being executed. And if the task hasn't been executed, it just stays in the active pool. But once it's ready, then it's going to transition to the completed pool. And this is also the point where at least RPU will go and investigate what are the output data, what is the output variables coming from this task that you finished executing, and it will update the stage of all the tasks that depend on it, and possibly move them from the submitted pool into the ready pool, ready for schedule. So this is what is basically happening, is that each task has a list of output data, and it's going to scan to the list and then update all the tasks in the submitted pool that use that particular output data as their input. So you can imagine that how this kind of approach would at least guarantee that in some point we will actually end up moving all the tasks through this whole chain into the completed pool. And the way we can actually try to help the runtime system do it in a smart way is that we will define priorities that when the tasks are picked from the ready pool to be executed, it will actually try to first pick those tasks that has the highest priority. But beyond that, this is pretty much what the runtime system end up running underneath. If you have something like GPUs, then at this point, it will try to do something smarter. It might, for example, figure out that this task might run faster on a GPU or a CPU and select the computational resource based on that information. So it can be a bit faster, but underneath it's still the same logic. And the key is pretty much here, when the tasks are moved from ready to active, this is where we must have some level of intelligence implemented. And usually it means that it's the programmer who has to specify some form of priority. So the runtime system knows in what order it should move tasks from ready pool to active pool. And then there is one key topic that needs to be discussed called the task granularity. And task granularity basically tells us something about how large the tasks are. And usually this means in terms of execution time, and it also usually tells us how many tasks there are. And this can be a really important factor for performance for three primary reasons. The first reason is that the runtime system will introduce some extra overhead when it's trying to figure out how the tasks are dependent on each other, and when it's also doing the scheduling. This will add some additional overhead. Extra computer resources are needed to do these operations. Then quite often it happens that when you go and start cutting your algorithm into tasks, if the tasks are large, then you will actually end up having better performance inside the task. And this might happen, for example, so different kind of cache effect might be happening. That if you have bigger tasks, then you can actually load it in a much efficient way to the caches in a smaller blocks and get performance. And you have very tiny tasks, then there is this all sort of extra things that you might be aware of, the concept called loop unrolling. So it's a similar thing when the tasks are slightly bigger, you will tend to get a slightly better performance out of them. But that doesn't mean that the algorithm itself will perform better. It just means that the tasks themselves will perform better. And then the third thing is that depending on how many tasks you are, that is going to affect how many tasks are ready for scheduling at any given time. Just an example, let's go back to the earlier example here where we had divided the matrix into these blocks. And for each block, we define some for tasks that operates inside the block. And then you will end up operating through the entire algorithm in iterative manner. If instead we would make this block smaller, now individual operations that happen inside each block, there is less computations to do, and therefore the tasks become smaller in terms of execution time. But the number of tasks, clearly, it's going to grow a lot. And we say that in the first example, the task granularity is very coarse. So the large tasks are very large, and there are a fewer number of them. And on the other end, we have the task granularity is very fine. We have a lot of very, very tiny tasks. And in this instance, if we make the task granularity very coarse, we will have three things happen. The first is that the number of tasks is very small, therefore there is practically no overhead from the runtime system at all. The second thing will happen is that each task will actually perform slightly better because this algorithm actually relies on some library called BLAS, and BLAS usually gives you better performance when the operations are larger, excluding this diagonal block here, but I will now just ignore this minor detail. And then the number of tasks that you actually have here at any given time ready for scheduling is going to be quite small. For example, here you can see that the number of tasks we can schedule at this point would be 9. If we move to the second case where it's very fine, then we will note the number of tasks we have in total is very large. And therefore, it's now going to take the runtime system much longer to figure out the data dependencies between the tasks and also go through these list heuristics to schedule the tasks. So we will get more overhead. Then for individual tasks, the performance will drop because you cannot benefit from techniques such as loop unrolling or different kind of cache techniques that well. But then the number of tasks you can schedule at any given point is going to be much larger. So if you have a lot of CPU cores, you can keep more of them busy more of the time. It's again a good thing. But it's usually a key thing that we have to balance the task granularity in some manner. So in this visualization here on the horizontal axis, you can see task granularity. It's just some sort of generic measurement. So this is not from any real algorithm. This is just all theoretical. So here you can see the task granularity comes from very coarse to very fine. And then we have the runtime that goes from 0 to, let's say, 100 of something, seconds, minutes, days. It doesn't really matter. And what you note here that if the task granularity is very coarse, then you don't actually get that much parallelism here in the blue. So you're pretty much just running on a single core. But when you increase the number of tasks to become large enough, then you will start actually getting more and more cores busy until you end up saturating all the cores. And after this point, you have reached the maximum level of parallelism conceivable. Then when you look at here, red is how efficiently each task is running. And when the tasks are quite large, they run at very close to the peak efficiency they can run at. But when you start making them really tiny, you note that the task efficiency will actually drop. And when the tasks are really, really tiny, you are just mainly using all the optimization technique you could implement inside the tasks. And then we have the overhead. When the number of tasks increases, we will gradually start see a situation where the overhead starts becoming the dominating factor. And when we add all this together and look at the overall runtime for the algorithm, you know that at the beginning, nothing really happens because the tasks are reasonably big, but there are so few of them that all the CPU cores are idle. But once we start seeing that the level of parallelism start picking up, we will start seeing improvements in the performance. And these improvements keep happening until we level down here. And this happens for two primary reasons. First, we are actually, all the CPU cores are very busy, and we can actually see that if you make the task any smaller, the tasks themselves will start performing worse. So you will actually see that if you make the task friendly do fine, you will actually start losing performance first. And then what happens is that the overhead starts kicking in, and you can actually end up a situation where your task-based algorithm running on, let's say, 28 cores on a Kebnekaise will actually run slower than it would run on your laptop on a single CPU core. So you have to strive this balance point in some way. So, and then in the end, I just brief summary of the benefits of the task approach. The first one is automatic parallelism. So if the task graph has some potential for parallelism, then at least theoretically, the runtime system should be able to discover this parallelism and take advantage of it. Of course, this is not always the case. You can go and construct your task graph in a very naive way and lose some of this parallelism. But you can help the runtime system with priorities to help the runtime system discover this parallelism. Then one major benefit is that it allows us to reduce the number of synchronization points. So of course, in algorithms, they have data-derived synchronization points. So you have to get the data to advance. So there is some level of synchronization always happening. But usually it happens that when you're writing your code, it just gets really complex. So you end up adding synchronization points to your code that do not actually arise from the underlying data. They are just there so you can be sure that you have executed all the previous steps. So you can safely move to the previous step. And it's the second type of synchronization points that you do for implementation reasons that you can remove when you move to task-based parallelism, because the fact that the runtime system settles the tasks in a manner that it respects the data dependencies, task dependencies, guarantees that all the operations that came before have been executed before the new operation can start. Then we have a better load balancing because the runtime system can dynamically react to various situations. Situations in changes in load balancing, you don't have to do it yourself. Then there is something called shortening the critical path. And this is that you remember early example where I had these nested for loops showing that the critical path is pretty much the whole length of the algorithm. Whereas you consider the task graph, you can see that you only have to execute a sub part, only a certain section of the task graph. And this is called, here you are shortening critical path, and therefore you get a smaller, lower bound for the runtime of the algorithm, and therefore potentially better performance. Then you could use GPUs and accelerators, and this is mainly for StarPU. And what happens there is that you basically provide an implementation for the task for a CPU and a GPU. And after that, you don't have to care about how the data is moving around. The runtime system will do it for you. And this makes things much more modular. And finally, also related to StarPU, you can even do a distributed memory computations in a task-based manner. Because once you know the task graph, you know what operations are being executed and what data is needed, and you know where the data is stored. Then from this information, you can automatically induce the communication pattern because you know what computations happen and what data and where the data is located. You can get the MPI send and receive function pairs out of that information. And this concludes this lecture here. And I think at this point, if anyone has any questions, I will go through. You can ask them right now. I see that there are a couple of questions in the Q&A. I will go through those. And then I will take a small break for myself so I can recover some of my voice. And then I will be spending the rest of the morning talking about OpenMP. So please ask any questions if you want or write in the Q&A.